Good morning, class. Today we want to look at surface area of prisms. This is after our previous topic that we derived the relationship for calculating the area of sectors, area of plane surfaces. So we want to use that particular application in finding the surface area of what we call prisms. So what is a prism? Now we have said that the surface area of three-dimensional objects can be found by the sum of all the areas of its plane surfaces. And when we talk about three-dimensional objects, we mean objects that can generate volume. Objects that can generate a volume is known as a prism. We have several types of prisms. We have several types of prisms, and we are going to just mention a few. A cuboid is a prism. A cube is a prism. Triangular base prism, we are going to look at this. They are also known as wedges. Cylinders are prisms. Cones are prisms. And many more that we are going to define. So each prism derives its name by the type of the edges that make it. For example, if it is a cone, we know that the base of the cone is circular, and that's why the curved surface is also circular, a part of a circle. Cylinders, we know the base is circular, and also the curved surface is also circular because of the circular base. Triangular base prisms, these are just prisms whose one of the planes or two of the planes are triangular in nature, as we are going to see. For a cube, all the surfaces are equal, are similar, and then for a cuboid, two plane surfaces are also similar. So we can use that information to now look at the surface area of each particular prism. So to start with, we have a cuboid. And we have said that for a cuboid, two of its plane surfaces, which are opposite, are similar. For example, in this figure here, we have plane AFGH being similar to an opposite plane BCDE. Are we together? Similarly, we have plane A, B, C, H being similar to plane E, D, G, D, E, F, G. D, E, F, G. Lastly, we have two planes that are similar. We have plane A, B, E, F being similar to plane C, D, G, H. So in total we have 6 planes. 2 are opposite and similar. And therefore, we can now apply the formula for finding the areas of plane figures to find the sum, because we have said that from the above diagram, it is observed that the object has the following plane surfaces, as we have indicated. In total, there are 6 plane surfaces making the object. So we can use this information now to calculate the surface area of the cuboid by applying the formulae that we learned in calculating the area of plane surfaces. Let's look at that. We open the net of this particular solid, and when we talk about the net, we just assume that it is an open object. It's made of several plane figures. So look at the net of this. You can see that we have opened the net for this particular solid object. Now, if you look at the planes that has made the object, they are just basically rectangles. So we use the formula for finding the area of each particular rectangle, and we sum. We add all the areas, and the sum of all the areas will be the surface area of the solid object. So let's proceed and see. So all these are right-angled right objects. We have the plane A, B, E, F, the plane A, B, C, H, the plane A, H, F, F, Y double F, F, because when we close it, F and F will come together. Here, E, D, D will come together. Then F, G will come together, which is this. H, H will come together. C, C will come together. So that is how we make our net of the three-dimensional object. So let's look at an example. So class, you can see now we have opened the net for this particular cuboid, and the cuboid is made of rectangular plane surfaces of the dimensions indicated. Like we have a rectangle of 8 by 3. We have a rectangle of 8 by 5. We have a rectangle of 5 by 3. Those are the rectangles making the plane figure. So we are able to use the information of areas of plane figures to calculate the area, the surface area of the cuboid. So we are going to have two into 8 times 3. Why is it 2 into 8 times 3? We have plane ABCH being similar to plane DEFG. So there are two which are similar. So when you calculate the area of this plane here, it is similar to another plane which is up here. So that's why we are multiplying by 2. Plus 5 times 3, and we have two such planes. There's another one here. So there are two. So if you find the area of this plane AFGH, it is similar to another plane BCDE. That's why we are multiplying by 2. Two into 8 times 5. How do we get that? We have two planes, 8 by 5. We have this plane here, 8 by 5 as our plane. And then we have another top. This one here. Stopisha kidogo. And another top plane which is 8 by 5. So we multiply by 2. So upon multiplication, we obtain (24 times 2 plus 15 times 2 plus 40 times 2). So you get the area as 158 centimeters square. That is the total surface area of this particular solid cuboid. Let's look at another example. So class, you have seen we have now opened the triangular based prism. So you can see that from the original figure we have A, B, C, D as the base, which is this one here, A, B, C, D. Then we have the plane, the slant plane, which is A, B, F, E, and this is the same plane, A, B, F, E. We have other planes, the hidden plane, which is C, D, E, F, and the same plane is here, C, D, E, F. We have the triangular planes, which is A, E, D, and it is here, A, E, D. The last plane is the other hidden triangular plane, which is B, C, F, and here we have B, C, F. So we have managed to open the net of this particular prism, and therefore it is now easier to calculate the area of this surface area of this particular prism by applying the formula for finding the areas of plane figures. So here we have triangles and rectangles. So we'll have the formula for finding the area of the triangle and the formula for finding the area of rectangle. So let's see how we get the surface area. So we have 2 into a half base times height. This is the formula for finding the area of the triangular planes. And we have 2 similar of them. That's why we are multiplying by 2. Then plus length times W1. Now, why are we adding W1 plus W2 plus W3? It's because the widths of the rectangular planes are different. We have the first plane in this particular prism with the width of 5 centimeters. Length is 10 centimeters. Then we have the second plane which has width of 4 centimeters, but length is 10 centimeters. Then we have the third plane with width 3 centimeters, but the length is 10 centimeters. That's why we are having W1 plus L1, LW1 plus LW2 plus LW3. So when we substitute for those numerical values, we obtain So you can see, class, that we have 2 into a half times 4 times 3, which is the area of the triangular faces, plus 10 times 5, plus 10 times 4, plus 10 times 3. So let's simplify and see what we get. We get 132 centimeters square as the area of surface area of this particular triangular prism. It is 12. If you multiply this by a half 1, by 2, 2, 2 times 3, 6 times 2, you get 12. 10 times 5 is 50. 10 times 4 is 40. And 10 times 3 is 30. So if you add this, This one is 90 plus 30, 120 plus 12, 132 centimeters square. That is the area, surface area of the plane, the triangular prism. So let's look at an exercise. So we have opened the net for this particular prism, and therefore we are now able to calculate the surface area by applying the formula for finding the areas of plane figures as we have already defined. So you can see this is the net of our object, and we can now use the formula for finding the areas of the surfaces of the figures to find the total surface area of our prism. So class, you can see we have already we have already known the formula to use in calculating the total surface area. So by substitution, we get a half times 12 times 5 times 2 because of these triangular planes ADE plus BCF. Those are the planes we are finding their areas. Then plus 10 times 12. 10 times 12 is ABCD. Then 10 times 13. 10 times 13 is the plane ABFE. Then finally we have 10 times 5, which is the plane DCFE. DCFE is 10 times 5. So upon simplification, we obtain we obtain 360 meters square as the total surface area of this particular prism. Because this is a half, 2 into a half times that, which is 30 times 2, 60. 10 times 12 is 120. 10 times 13 is 130. And then 10 times 5 is 50. So upon addition, we get 360 meters square as the total surface area of the prism. Let's look at another example. So class, you can see that from this particular prism, we have two triangular opposite faces, and they are joined at the vertex by a straight line. So this is a kind of a wedge that now we use, but if you look at this particular end faces, which is triangular, they are made of what we call an isosceles triangle. So because we have been given the edges of the isosceles triangle on the base, it is possible for us to find the perpendicular distance using Pythagoras Theorem. And from there, if we know the perpendicular distance, we are now able to calculate the area of the triangle. Of course, we have other formulae for calculating the area of a triangle, but in this case, we shall use the more simpler method, which is just a half base times height. So we want to look at find the perpendicular height of this particular triangle. So we use Pythagoras relationship to determine that. So by use of Pythagoras relationship, we'll get five squared minus 4 squared So the perpendicular height of this particular isosceles triangle is 3 meters. And therefore we are now able to use the formula we've learned earlier on to calculate the surface area of this particular wedge. So we insert in the formula we derived, and we get now the area as we get area as 168 meters square. So you can see it is easier to, very simple to calculate the area of total surface area of solids. And the easiest way to calculate the surface area is first of all to open the net. When you open the net, it becomes very easy to calculate the surface area because you are dealing with the plane surfaces. So remember in our introductory note, we say that a solid object is made of plane surfaces of different shapes. So whether it is a shape made of triangular faces, rectangular faces, circular faces, cylindrical surfaces, you are able to use the derived formula that we have learned in the calculation of areas of plane figures to calculate the surface area of solid objects. Let's look at further examples on the same. So class, you can see that this is now a square-based pyramid. Why are we calling it square-based pyramid? It's because the base is made of a square plane object surface, and the slanting faces are triangular. So we open the net. That is the first procedure to calculate the area, total surface area of this square-based pyramid. So open the net of the object. Once you open the net of the object, you are able to visualize the plane faces that are making this particular object. So in this particular net, you can see we have 4 similar triangles. And the 4 similar triangles are ADE, CDE, BCE, and ABE. Those are the 4 similar triangular faces that we have, of whose dimensions are, the base is 5 centimeters, and the perpendicular height we have been given as 8 centimeters. So we are able to calculate the surface area of that particular square-based pyramid. So the general formula we use for this is 4 into a half BH plus L times W. Now where 4 signifies the area of the plane triangular faces, because we say they are similar. They are similar, and if they are similar, we just get the area of one, then multiply by 4. So we'll get 4 into a half times 8 times 5 plus 5 times 5, because the base is a square, so it will be 5 times 5. So surface area you get as 105 centimeters square as the total surface area of that figure. That formula you also apply it when we have rectangular based pyramid, as we are going to see the example. So you can see we have a rectangular base pyramid of the following dimensions. The base is made of 12 by 5 and the slant heights are 13 centimeters each. So we open the net. Class, this is the net of that particular pyramid. So we are able now to apply the formula we have learned in calculating the area of plane figures to calculate the area of the planes. But this time you can see that we have different triangles in this particular figure. Triangle ABE is similar to triangle CDE. And then triangle ADE is similar to triangle BCE. They are different. And therefore, you must find the area of each triangle separately. There are two which are similar. So we shall have total surface area being given by two into a half B1 H1, where B1 is the base of this triangle ADE, and then B2 is the base of triangle ABE. LW is the area of the rectangular base. But remember, here we are not given the perpendicular heights. And therefore, still we use Pythagoras relationship to find the perpendicular heights of those triangles. But you remember that other than a half base times height, we say there are other formulae for finding the area of triangles, but they are longer. So we are going to use the more simpler formulae to calculate the area of the triangular face. For this one here, so we calculate the area of that, the height of that triangle by use of Pythagoras relationship. (13 squared minus 2.5 squared) the square root of 162.75, that is H1, for H2, H2 is equal to 13 squared minus 6 squared H2 is the square root of 133, which we now can use our calculator to find the square root, and then we come and substitute in our. Now we have found the perpendicular height of triangle ADE, which is 12.76 centimeters, and triangle ABE, which is 11.53 centimeters. So we are now able to substitute these values in our general formula to calculate the total surface area of the rectangular based pyramid. So class, you obtain 2 into a half times 5 times 12.76, 5 times 12.76, plus 2 into a half times 12 times 11.53, 12 times 11.53, plus 12 times 5, which is the base area. So upon simplification, we obtain by calculation So you get 262.16 centimeters square as the area of that particular rectangular based pyramid. So with that, we can now calculate the surface area of any prism comprising of different plane surfaces. So let's move on our last subtopic today, the surface area of cylinders. A cylinder comprises of top and bottom circular parts, circular surfaces, and what we call a curved surface. So when we open the net of a cylinder, this is how it looks like. So class, this is the net of a solid cylinder, and therefore we can use the formula that we have derived, the premises and correlation of what we have derived earlier, to also find the surface area of a closed and open cylinder. So the top part is circular, and we can find the area of the top part, which is circular. We can also find the area of the base, which is also circular, and then find the area of this particular rectangular curved surface. And to find the area of the rectangular curved surface, it is important to bring into focus the circumference of the circle we learned earlier. You remember that the distance, if we have this one as A, B, C, D, the distance AB is basically the circumference of the circle, because when we curve this round, it should be able to fit into this circle. So in essence, when we find the circumference of the circle, it's as well as finding length AB or length CD. So it is important to note that. So let's first of all find the length AB by appreciating that the length AB is equal to the circumference of the circular part, circular surface. So So our length L is equal to 2 pi r, where 2 pi r is the circumference of the circular part. Two pi r squared. Why? The first circle, which is our circle number 1, top part, and the second circle, which is circle number 2, will have, and they are similar, will have area as pi r squared. And since they are similar, we multiply by 2. That's where we are getting 2 pi r squared. Our area of the curved surface is given by A2 is equal to LH, where H is the height of the cylinder, and L is the length, which is equivalent to our curved, of the circumference of the circular base. So the curved surface now is given by 2 pi RH, where 2 pi r is the length of the circular, the curved surface. So from there now we can get the total surface area of the cylinder. We get 2 pi r squared plus 2 pi r h, where this is the sum of the area of the top and bottom part, and this is the area of the curved surface. Now, if the cylinder is open, if it is open, surface area is given by pi r squared plus 2 pi r h. Why? Is because the top or the bottom is not there. So we just use one of the area of the circular what? Of the circular plane bases or the top. And that one we can now apply, use that information to solve some numerical problems in life. So let's look at one example before we end. It is important that we open the net of that particular cylinder and then we do the mathematical substitution using the formula that we have derived. And remember, here we have been given diameter, so you must, when you are calculating the area, convert your diameter into radius. So you obtain total surface area as 377.14 centimeters square. So with that, class, it marks the end of our lesson today. When we meet next time, we look at surface area of other objects and prisms, which we call composite figures. Thank you so much.